Okay, we'll get started here. I hope you're going to find that today is, at least the first part, the polynomial functions, you're going to find to be relatively, I don't want to say easy, I hate saying easy, but most students don't struggle with this concept. Rational functions a little bit messier, and then exponential and logarithmic functions, which we cover next class, most students struggle with those just because the notation's weird. All right, so y'all ready? Did y'all have a good weekend? You okay? All right, tonight's homework assignment is going to be problems that I put up on the board. So you're not going to do the problems out of the book, right? For polynomial and rational functions. We're about a day behind right now. We're supposed to be starting exponential functions today. So just FYI. Okay, here we go. So we have studied two types of functions. I showed you last class there's 6 types that we look at. Linear functions look like f of x. That lets us know we have a function. That means it passes the vertical line test. And then it looks like mx plus b, where m was the slope, b was the y-intercept. And then here's a specific example of a linear function. F of x equals 3x minus 4. And we know that when we graph it, we'll get a line, right? Then we have quadratic functions. And quadratic functions, the standard form was ax squared plus bx plus c. Here's a specific example. And we know at least that this parabola would open up because we have a positive 3 here, so we know it would look something like this. Now, I underlined some things in green here. And what is it about those green parts, I guess? I'm trying to get you to see what do they all have in common. They're all just numbers, right? So like when you have a specific example of a line, you have to replace that m with a number and that b with a number, and then you can actually draw the line. If I replace the a, the b, the c with numbers, a, b, c, then I can actually graph the parabola. But the general form of a line in a quadratic function or a line in a parabola, we use letters to represent those arbitrary numbers, right? Now, there's a reason why I'm telling you this, because now I'm going to show you what a polynomial function looks like. So a polynomial function looks like this. What does poly mean? Poly? Multiple, many, something like that. Many nomials. Now, each one of these, this is what we call a monomial. This is a single nomial. This is a nomial. This is a nomial. This is a nomial. This is a nomial. Polynomials means many of these. All right? So here we have 2 of them, don't we? We could say we have this is what we call a binomial, bi meaning 2. This is what we call a trinomial, meaning 3. And then once we go past 3, we just say polynomial because many, right? We could have 4, we could have 5, we could have 6. It doesn't matter. So here's the notation we use for a polynomial. I'm going to do this a little bit backwards. I'm not going to give you the general form first. I'm going to give you a couple of examples first. All right? So here are a couple of examples of polynomials. All right, first one, f of x equals x cubed minus 4x squared plus 7. Now that has 3 nomials. It has monomials. Single is monomial. We have 3 of them, don't we? But it's not the same as a quadratic function. Why is it not the same? It's cubed, right? X cubed instead of x squared. So it automatically it fails to be what we call a quadratic function. But it still has multiple monomials. Okay, so it is a polynomial. Here's another example. X cubed minus 9x squared plus 24x minus 15. So again, many nomials I have 4 of them, don't I? 1, 2, 3, 4. This is not a quadratic. Quadratic functions, the highest power of x that you see is 2. Here we have 3 again, right? Now, do we have to stop at 3? We can have a polynomial that has x to the 4th. I don't have one here, but oh, here we go. X to the 5th minus 4x cubed plus 5x plus 1. There's another example of a polynomial. And there really is no restriction at all on how high this number can go. You could have a polynomial where you have like x to the 200th power, plus 12x to the 99th power. There's no limit to how high this number can go, and you do not have to have every single power of x appear. So notice I have x to the 5th, but I don't have x to the 4th. I have x cubed, but I don't have x squared. I have x, right? You do not have to have them all appear, all right? These are all examples of polynomials. And the question becomes, what do they look like? And I started talking about this at the end of class last time. Like, I was showing you why certain functions are good. These two are good, but there's others that model different behaviors. So does anyone remember what polynomials kind of look like? Or remember the example I gave for a polynomial? Like a wave. Like the stock market is what I gave as an example. So all polynomials look like this. I'm still holding off on giving you the general form, okay? I'm going to give it to you, but just hang tight. Okay, so the graphs of polynomials have the following characteristics. They're smooth. They're curved if power is 2 or more. Meaning we're going to have a curved graph. It'll be smooth, it'll be curved as long as the power we have here, the highest power, is bigger than 2. 2 or higher, all right? And that's pretty much it. Smooth means there's no like sharp corners or jagged edges or breaks in the graph. So if I imagine drawing this, here's one example. I could have something like this. Right? That's smooth, that's curved. I could have something like this. I could have... Now look at those arrows. The arrows at the end are actually kind of important. The arrows tell you the behavior of the graph if you were to continue drawing that function in that direction. So this arrow down here is kind of like the arrow we put on the parabola, where the implication of the arrow was that it kept on going up and to the right. This one would be up and to the left, right? Same thing with these arrows here. This arrow means it's going to go down and to the left, up and to the right, up and to the left, up and to the right. Yes? We actually have a technical name for this. We call it the left and right hand behavior. I'm going to write this on the board later, but that's going to be your task. Your task is actually going to be able to identify the left and right hand behavior of polynomial functions. All right, so they're smooth, they're curved. Now, you ready for this general thing? This is the thing that most people start to kind of get nauseous when I put this on the board. So here we go. I'm going to put it right here. I need a little bit of room. So the general polynomial function, here's how we write it. A subscript n, x raised to the n, plus a subscript n minus 1, x to the n minus 1, plus a subscript n minus 2, x to the n minus 2, plus dot, 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 plus a sub 2, or let me do it this way, a sub 1, x to the 1 plus a sub 0. Right? That kind of makes you nauseous just looking at that? It's pretty, huh? So this is one of those times I remember as a student when I first saw this, which, by the way, I was not always a math major, okay? So I didn't enjoy math in high school. I didn't enjoy math too much in the beginning of my college career. So there was a point where I looked at this and I wasn't excited, like I was upset about it, right? So what makes it so upsetting is all those damn subscripts and letters and stuff, right? It's a little bit overwhelming. But there's a reason why we write it this way, and it's not just to make you hate math, all right? Here's why. I'm going to underline some stuff in green. Okay, this right here, this right here, this right here, this right here, and this right here. What do you think all those really are? I mean, what do you think this represents? Well, the whole thing together is a monomial. But go back over here. Look at what we had here. I had mx plus b, right? And we said that the m and the b were just numbers, right, that we're going to plug in. Here we had ax squared, bx, and then c, right? The a, b, and the c were just numbers. So here, what I'm underlying in green there, those are just numbers. Arbitrary numbers. So why write it that way? Why in the hell would we do that? Why not just say like ax, b, c, d? Why not just use letters instead of using those weird subscripts? I'll offer 3 points to anyone who can tell me why we might use that instead of, yes, very good. Because in our alphabet we have what, 26 letters? And I just told you that the highest power on this is not limited, right? I could have x to the 200th power. If I had x to the 200th power and you tried to use a, b, and c, it would look like this. A x to the 200th plus b x to the 199 plus c x to the 198. And what's going to happen? You're going to run out of letters, aren't you? Right? So instead what we do is we use this subscripting. And here's how that works. If we had a 200th power polynomial, then we would call this first piece, we would call this a sub 200. This one would be a sub 199, a sub 198. So this is like the 200th number in front, the coefficient. This would be the 190, the number in front of the power of x, that's 199. Does that make sense? And you never run out of letters. I mean, that's the whole reason we do it, all right? We don't need to know this. I'm just trying to get you to understand why that formula looks so bad. So let me write down what we really need to know. We need to know that a sub n minus 1, all those things all the way down to a sub 0 are numbers. And then we also have that a sub n cannot be 0. If a sub n, if this first number is 0, then this is no longer x to the n. So remember we said that here a couldn't be 0 because then it wouldn't be a quadratic? Same thing here. This is what we call, right here, this is called a polynomial function of degree n, or an nth degree polynomial. So the n up here is your highest power. N is your highest power of x that you see. Whatever the highest power is called the degree of the polynomial. So if this is n, if that's the biggest power, do you see how this one is one less than it? So if that's like 100, this one would be 99, this one would be 98, 97, 96, and so on and so forth. So the n is your degree, and then the a sub n, this right here, is called your leading coefficient. Now, believe it or not, Knowing the degree of a polynomial and knowing the leading coefficient tells you a lot about what the graph looks like. So what I'm going to do now is I'm going to put a couple of polynomial functions on the board, and I'm going to ask you to identify the degree and the leading coefficient. This is the part I said was really kind of easy. So let's, for this example, find the degree, and I'm going to put LC from now on for leading coefficient, okay? LC. Find the degree and the leading coefficient of this function. F of x equals x cubed minus 4x squared plus 7. So what is the degree of this polynomial? Well, is it a polynomial function? You have to know that first, right? It is. And what is its degree? What is the degree? Is the highest power of x that you see, which is just the number 3. Okay, so this is just 3. So it's a third degree polynomial function. What is the leading coefficient? So the leading coefficient is the number that's in front of that highest power of x. So what is the number sitting in front there? The number, 1. So there's a number, there's a 1 there. We don't write it normally, right? So this has a leading coefficient of 1. You do not include the x in the leading coefficient. All right? Simple enough? Okay, let's do another one. How about f of x is negative 4x squared plus 8x to the 5th minus 7. Is that a polynomial function? Yes. Yeah, you see separate terms, right? And you see powers of x in there. Okay, what is the degree? 5. Good. Degree is 5. I was trying to trick you. The degree is the highest power of x that you see, which is 5. And then what is the leading coefficient? 8. It is the number in front of the highest power of x, so the 8. Yes? Okay. All right, now the reason we're doing this is because of the following thing I'm about to put up here. Left and right hand behavior of, I'm going to put polyfunctions, polynomial. Left and right hand behavior of polynomial functions. All right, here's what we know about polynomial functions, all right? All polynomial functions will do one of 4 things when it comes to the left and right hand behavior. So here are the 4 possibilities, and I'm going to draw them in a table. So just copy this table down. All right. All polynomial functions are either going to go up on the left and up on the right, almost like a parabola. And then in the middle, it might do some wiggly stuff. So it might go, like this, and then that's what I'm talking about. On the left, it goes up. On the right, it goes up. In the middle, I don't really know. Every polynomial function is a little different. So what I like to do is put a question mark here, that the middle, we don't really know what it does. But in terms of the left and right hand behavior, it's either going to go up on the left, up on the right, or it could go down on the left, down on the right. And in the middle, I still don't know. And then what do you think are the other possibilities? There's 2 more. Up on the left, down on the right, or down on the left, up on the right. Yes? So I'm going to put this one here first. Down, question mark, up, or up, question mark, down. Do y'all understand these 4 scenarios? All polynomial functions have to do one of those 4. Now the question is, how can you determine which one it is? And it turns out that you can use something called the leading coefficient test. And that's why I had you identifying these things a second ago. All right, so you see these two possibilities right here? Right here? These two possibilities will only happen if the degree is even. If n is even. Okay? So if n is even, it's going to be one of those two. If n is odd, then it's one of these two. When I say n, what am I talking about?
Degree.
The degree, right? So if the degree is even, it's going to be one of these two. If the degree is odd, it's going to be one of these two. So looking back at these two polynomial functions, what you can tell me so far is that this one up here has an odd degree, right? That means that it's going to either look like this or like this. Now to figure out which of these two it's going to be, we look at the leading coefficient. If the leading coefficient is greater than 0, that means positive, right? I'm going to put positive under here. Then it's going to be you're going to be along this row. If your leading coefficient is negative, less than 0 or negative, then you're going to be along this row. Make sense? So it's kind of like all polynomial functions either do this, 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 or this. That's it. That's the only possibilities. Okay, so what does this one do? What's the end behavior of this polynomial? Left side goes down, right side goes up. And you can tell because odd, that put us here, right? And then positive number put us here, so that had to be this one right here. Okay? So I know from this goes down, question mark, up. What about that one? What's the degree? 5. What's the leading coefficient? 8. So odd, positive again. Same thing, right? It would do the same thing. The left would go down, the right would go up. Now we're not saying that these two graphs look exactly the same. We're just saying that the end behaviors are the same. That's all. In the middle, the question marks mean that they're going to be smooth and curved in there, but where they actually make the curves is different for each one. Okay, so let's do one more example. Can you tell me for this one to describe the end behavior of f of x equals negative 4x to the fourth plus 3x cubed plus 1. Tell me what the left and right hand behavior of this one would be. And when I ask for this, all you have to do is draw that little thing with the question mark, and that makes enough sense to me.
So both going to go down?
Both sides down. Okay. So you're doing an even degree, right? What's the degree of that polynomial? 4. So this is n. And then what's your leading coefficient? Negative 4. So you have an even degree. You have a leading coefficient that's negative, so you've got to be right here. So it's going to go down, down. Down on the left, down on the right. Is that straightforward enough? I'm sure you'd love for your next exam just be 20 of those and you're good to go, right? Okay. Unfortunately, that is not going to happen. All right, so now what we're going to do is we're going to move on to the question mark part. This part. How do we determine what's happening on the inside? And that in itself, the question of how to determine what the inside of this looks like, is probably about a full week and a half in a true math 1414 environment. We spend at least 2 full class periods graphing polynomial functions because there's a lot to do. What we're going to do here is a very, 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 very watered down version of that. And we're going to skip a lot of the hard stuff, okay? I'm just being honest, that's what's going to happen, all right? So we have to kind of concede that when it comes to graphing polynomial functions in this class, we are going to be very limited as to how we can do it and what we can do. So when we have, let's say we have this example here where I tell you that we have, let me see if I can get one here. Yeah, we can do this. How about f of x equals x cubed minus 4x squared plus 3. Now you can tell me for that one the left and right hand behavior, can't you? What is it? Down on the left, up on the right. So this goes down and then up, odd, positive, right? Odd, positive. So if I wanted to know what this is, the inside piece, what I could ask myself to help me graph this is what are the x-intercepts? Does this graph hit the x-axis? Maybe it does. So think about why that would be important. Let's say that we had this, and let's say I told you that this graph hit here, and here, and let's do one more. Let's say here. What if I told you that it had those 3 x-intercepts? Then you could pretty much draw it because you know that the left side goes down. So you know that at this point you've got to go down, right? And on this side you've got to go up. So the inside, if I have to hit these points, could look like this. This is probably a very good candidate for what it looks like. Would you agree? Now it turns out it's not that easy. That sometimes you could have this happen where you actually come up and just kind of bounce off that point, and maybe you bounce off this point again and then go up like that. That could happen. There's a lot of different scenarios. And in a college algebra course, we have to look at that very carefully. All right? Again, we're not going to do that. So what we're going to go for here are the x-intercepts. We're going to try and find x-intercepts. So for this problem, I'm going to continue here. Let's find the x-intercepts. How do we find x-intercepts? We set that function equal to 0, right? So we set that to 0. Oh, I forgot an x on the end of this. Sorry, there's an x out here. Right there, x. We set this equal to 0. Now, I intentionally designed this problem so it would work out. If we're trying to set this equal to 0, that means we have to take this side and we have to factor it. Okay, so here we go. How do we factor this? So what's the first step to factoring that?
Take an x out.
Take an x out. That's called greatest common factor. So if I pull an x out, I'm left with x squared minus 4x plus 3 equals 0. Now look at what's in the parentheses. This is a quadratic, and this factors. So how does that factor? Well, this is where, remember this thing from earlier in the semester? You made that little thing and do your numbers and you do all that. Does that look familiar? Yes? Okay, I'm not going to show the work, but we could take this and you could figure that this turns out to be x minus 1 times x minus 3. And that equals 0. So that step from here to here is something that I would have to trust that you could do. This one? They all have a common factor of x, right? This has 3 factors of x, 2 factors, a single factor. So I pull out a greatest common factor first, which is a single x. And it reduces all the x's by 1 factor. That's the first step for factoring. Then this is a quadratic, and we can factor using what we call the AC method. Now, once you have this broken down, you have 3 factors, don't you? And you can set each factor equal to 0. So if I set this factor equal to 0, first factor, set the second factor equal to 0, and set the third factor equal to 0, I will come up with 3 different solutions. And they are what? 0, 1, and 3. I'm going to box these. These are my x-intercepts, right? My graph hits the x-axis at 0, 1, and 3. And now for the tricky part. Let me try and draw this graph right now. Is that okay? Okay, if I were to graph this polynomial function, I know that this must be smooth and curved. I know the left side must go down, the right side must go up. I know that the graph must hit at 0, at 1, and at 3. Right, that's what I know so far. I know this side has to go down, this side has to go up. But I showed you just a second ago that there were a couple of ways we could do the inside, right? Okay, so here's the weird thing. Do you see right here that we have 1, 2, 3 factors? You see those 3 factors? What I want you to look at is the power on each factor. So what is the power that's on this factor on the outside here? 1. There's a 1 there, right? What's the power on this factor? 1. And what's the power on this factor? 1, because it's x to the first power. All right, you see these numbers up here? These are what are called the multiplicity of the x-intercept. This is the multiplicity. So they all have a multiplicity of 1, right? So I'm going to call this, these are all called multiplicity. All right, so I'm going to write a little note here on the side about multiplicity. If multiplicity is odd, then cross through x-axis. If even, bounce off x-axis. Now this will become more apparent as I do a couple of more examples here. All right, let me try and make sense out of this. Let's come back to this x-intercept. We had an x-intercept at 0, right? Okay, so I know that my graph actually touches right here, right? My graph, that point is part of my graph. I also know that the left side goes down, don't I? Now, if I were to start to draw this, I'm going to move my finger away from the dot. I'm not going to go from this point down. I'm going to just do it about right here. I know my graph has to do something like this, right? Now, when I get to this x-intercept at 0, I need to know, am I going to actually cross through the x-axis when I draw it, or am I going to bounce off it, like hitting a wall and bouncing? And to do that, I have to go back up to where it came from and look at the multiplicity of the factor. That's a 1, right? If that number is odd, then I will cross through. So that means when I draw this, I'm going to have to cross, oh, I missed it. I have to cross through it, right? Look, and it's like we're in kindergarten here. We're just connecting dots with smooth curve here. So we're going to connect, I've got to get back to this one, right? This is at 1. So I go to 1. I go up to its multiplicity. What's its multiplicity? 1. That's odd. I'm going to cross through there also. So that means when I draw this and I curve back around, I must cross through the x-axis. Now I've got to get back to 3, right? And when I get back to 3, it doesn't matter how low you go here. Come back here, and when I get there, what am I going to do? Cross through, because again, the multiplicity is 1. It's odd. So I cross through, and if I cross through, remember what the right-hand behavior was? It was up. So our graph looks like this. That is the sketch. That is the graph of this polynomial function. Understand? Okay, now one question that you might have is, would you be wrong if you drew it like this? What if somebody drew it like this? would that one in red be counted wrong? Absolutely not. Both of those would be full 100% credit, because all we can do in this class is determine the left and right behavior, where the x-intercepts are, and whether or not we cross through or bounce off. If you actually wanted to know how high this peak was or how low this was, you would actually have to take calculus. And in business calculus 1325, which is the class after this one, we actually do go after these points and try and find out where they are. Because we want to know, if this is like a profit function, we want to know where that profit's the highest. Just like we did with the parabola, like the vertex, do the same thing here. Which, by the way, I made my schedule for, I've requested my schedule for the spring 2018 semester, and I am going to teach a 1325. So again, if you want to avoid me, avoid me. If you want to take the class, I don't remember what day it was. They did not offer a Tuesday, Thursday, 9:30 a.m. There wasn't one available for me to choose. So I picked something. I think it's, well, you know what? I take that back. I think I did pick a Tuesday, Thursday, 9:30 a.m. Either way, I'm going to be teaching at least one, well, only one 1325 in the spring, so long as nothing changes with the schedule. All right, that makes sense? There's multiple parts of this that are difficult. I think the most difficult part is the factoring. Because if you don't get your factoring done right, it's all going to be wrong, right? Okay, so let's try another one. And this is what, in a college algebra class, a 1414 class, they have to learn how to factor very complicated looking polynomials. And that requires quite a bit of time. So this example, we're going to sketch f of x equals negative 4x to the fourth minus 8x cubed plus 24. Oh, wait a minute, hold on, 4, 6, hold on, 6. I've got to get this right or else it won't work. Plus 32x squared. Let's do that. Let's try that. Let's see, 4, 2. I might have to change that 32, hold on. Well, let's just see what happens. Yeah, that should work. Okay, let's. So what first? What should I determine? Left and right hand behavior? What it does, right? So what does this one do? Down, down. So you have a degree that's even, right? A leading coefficient that is negative. So that means you're going to go down, down. So I know that much so far. Is that all right? You have to go to that table to look at the table that I drew. You need to learn how to read that table, because if it's odd, then things are a little different. Both sides don't do the same thing. Okay, now what? Find the x-intercepts? Okay, for the x-intercepts, I set the function to 0. So minus 4x to the fourth minus 8x cubed plus 32x squared equals 0. Now I have to very carefully pick these functions for you, or else they're not going to work. And I think I did okay. Let's see. What would you do to that? Take out a GCF first, right? That's always the first step for factoring. So you notice that we have what in common here? We have a 4 and x squared. Is it all right if I pull a negative 4 instead of a positive 4? Yeah, I would just change the signs. Now, we like to do that because if I pull a negative 4x squared out, I will have how many terms in here? How many things will be in here still? 3 of them, right? So if I pull negative 4x squared out of this, what am I left with here? Just x squared, that's it. If I pull a negative 4x squared out of this one, what am I left with? Plus 2x, right? And what about out of that last one? Minus 8, and that's it, right? See, I had to make this so that this factors. Does this factor? Well, you would have to use that little AC method, right? And it does. Again, this step from here to here is a big question mark, like how comfortable are you with that factoring? It's something that I gave you the first day you walked in here. You need to be able to factor, right? If you're still having trouble with this factoring, though, you should probably get a little bit of assistance, either from myself or from the tutoring lab. Factoring quadratics is never going to go away in any math class you take from here on out. You've got to be able to factor. So, anyone know what that is just right off the bat? X plus 4x minus 2. There we go. And now we set all of these equal to 0. So I'm going to set this to 0, set the entire thing to 0. I'm going to set this one to 0, and I'm going to set this one to 0. So what's the only number that I can square and then multiply times negative 4 to get 0? 0 itself. So this is 0. What about this one? Subtract 4 on both sides. So x is negative 4. And then this one, positive 2. Now, before I proceed, I'm going to look at the multiplicities right now, because I'm going to figure out if I'm going to cross or bounce at these x-intercepts. So let me start with this one, because I think this one is, these two are the easiest. What's the multiplicity here? What's the power on this factor? 1. That's odd, right? Odd tells me what am I going to do here? Cross through. I'm going to put a C under this. I'm going to cross through there. Okay? What's the power on this factor? 1. That's odd. I'm going to cross through here. Now, what's the power on this factor? 2. And that is an even number, and that means I'm going to bounce off 0. You all understand how I'm doing that? Common mistake that I see is that students will look at these numbers, their x-intercepts, and they will say, oh, 0 is even, so I'm going to bounce. Or they'll say, oh, 2 is even, so I'm going to bounce. You're not looking at the number to figure out crossing and bouncing. You're looking at the power on the factor. That's what determines cross and bounce. Understand the difference? All right, I'm ready to draw a quick sketch. I'm remembering it goes down, down. I'm going to plot my x-intercepts first. So 0, here I am. Negative 4, 1, 2, 3, 4, negative 4. I'm going to put a dot there. And then at positive 2, I'm going to put a dot there. That's the way I start my graph. Those 3 points exist. They are part of my graph. Now, as a reminder, both sides go down, right? So at this point, somewhere over here, my graph has to go down. And at this point, somewhere to the right, it's got to go down like this. Do we agree with that? Now you just have to connect all these together. So when I draw this, I'm going to draw it like I read a book from left to right. As I draw this up to this dot, what am I going to do when I get to that dot? At negative 4, I'm going to cross through. So I'm going to have to go up above like that. Now, when I get to the next x-intercept, which is 0, what am I going to do there? Bounce. So that means, you know, like a ball would bounce off the ground here. You're just going to bounce and come back up. And then you have to get back to this point at 2, and at 2 we cross. So, and again, it doesn't matter how high you go here. Whoa, that's good enough. See, that's my graph. Yours might look a little different, but we should both have the same major characteristics, which are where the graph is hitting the x-axis, where it's above the x-axis, where it's below the x-axis. Any questions? Sure? We're good? Okay. I'm going to give you a different problem, different type of problem. This one's going to look like kind of crazy when I put it up here. So here's a function. We've got x to the 5th, minus 3x to the 4th, minus x cubed, plus 3x squared. So we want to graph this. What's your left and right hand behavior here? Down on the left, up on the right. The degree is 5, the leading coefficient is 1. All right, x-intercept time. X to the 5th minus 3x to the 4th minus x cubed plus 3x squared equals 0. That's how I find x-intercepts. I set the function equal to 0. So what first? Greatest common factor? Okay, what is your greatest common factor? X squared. So put x squared, and then how many pieces are we going to have inside here? How many terms? 4 terms? What are they? X to the 3rd minus 3x squared minus x plus 3. There we go. All right, now this is the first time I've given a problem like this. What is the difference between what's in that parentheses and the problems I've done before? Yeah, we used to have 3 terms in the parentheses, right? Which we would use that AC method. Because this in here has been a quadratic the whole time. But now it's 4 terms. So how do you factor 4 terms? Grouping. Does that sound familiar? Okay, I'm going to do that on the side. Okay, I'm going to do grouping on the side. Okay, just looking at that. So I'm just focusing all my attention on just what's in the parentheses. How do we do grouping?
Take the first 2.
Look at the first 2, separate them from the second 2. So the way that I always show my students is I just have my students split this thing. Right after the second term, I have them split it. And then I have them pull a GCF, greatest common factor, out of just these 2. So what is common in just these 2? X squared. So I pull x squared. And then what am I left with? X minus 3. Because we pulled out the x squared here. We have an x. We pulled out this x squared. We still have minus 3. Yeah? Okay, now what are you supposed to do on this one? GCF again, right? Do we have a greatest common factor? Not really, but when we're done, we're supposed to have this match up with something over here, right? What's supposed to be over here? For this to work, what has to be here? X minus 3, right? That's what needs to be there. So this is not x minus 3, this is minus x plus 3. So what would we actually have to factor out of this to get this? Negative 1. Right? If we pull a negative 1 out of these, and then distribute back through, this would be negative x plus 3, and we'd be there. Now the next step is to rewrite this. How would this be rewritten? X squared minus 1, and then x minus 3. You could also write x minus 3 times x squared minus 1. Is this all right? Are we done factoring? What?
You get to put that first one back there? No, the x squared. Don't you have to put that back eventually?
No, this x
Oh,
squared
it's
minus
okay,
1
it's
is
okay.
this piece now.
Yeah.
But what I'm saying is this completely factored?
You have to distribute it?
That if we distribute, like multiply it, we're going to be back up here.
Okay. Yeah, you said multiple.
Do you recognize anything here?
X minus 3.
Anything special? X squared. What about this? Does this look like something special? It's quadratic. Think factoring. Is that a special thing? You're almost there. Difference of squares. This is a difference of squares. So, factoring is the Achilles heel of most students in college level mathematics. Most students cannot do well in college level mathematics because they can't factor. Factoring is something you're supposed to learn before you get here, right? In high school. It's not happening, but you know, we've been dealing with this for years and years and years. You should be able to identify that as a difference of squares. If you don't, then you just have to, you can say, I don't recognize it, and I'm just going to keep coming to class, and I'm going to keep not recognizing it, and then I'm not going to do well. Or you can go and get assistance on it. You can go to the lab and say, hey, I'm sitting in class, I don't feel comfortable factoring. I see a difference of squares, I have no idea what it is. And they can help you. That's what those free sessions are for, to try and get you up to speed. All right? I'm trying to help you recognize where your deficiencies are so you can go address them. Your other option is to struggle and then eventually realize you need to go back and take some refresher courses before you proceed. Okay, this is a difference of squares. All right, so this now becomes, what does this turn into right here? X plus 1 minus 1. And then what's still there? X minus 3. Okay, so what's in this parentheses turns into those three factors. You see that? So I'm going to rewrite this whole thing now. This is x squared, and then these things right here. These three things. X plus 1, x minus 1, x minus 3 equals 0. Now that we're there, we can set each of those factors equal to 0. So we're going to have 1, 2, 3, 4 factors. If you set each of these equal to 0, what are the solutions you're going to get? X is 0 here. What's the solution from this one? Negative 1, positive 1, and positive 3, right? You know what I'm doing here? Setting that to 0, that to 0, that to 0, that to 0, and you get those 4 answers. I'm almost ready to graph this, but I'm going to check for my multiplicities. I'm going to check for bouncing and crossing now. So what's happening here? Bounce or cross?
Bounce.
Bounce. We're bouncing because the factor is squared and that's even. What's happening here? Crossing because the factor is to the first power, that's odd. This one? Cross because the factor is 1, that's odd. This one? Cross because the factor has a 1, it's odd. Now I will draw. Placing all my x-intercepts, draw them out on my graph. I've got 0 here. I've got 1 here. I've got negative 1. I've got positive 3. These are my 4 x-intercepts. What should I draw next? my up-down thing, right? My left and right behavior. So what happens on the left side? I forgot, I erased it. Down on the left. So over here next to this dot, I'm going to draw like an arrow going down. And then over here to the right going up, I know it's got to do that, right? I'm crossing through every x-intercept except 0. At 0, I'm going to bounce. So here's 0, right? I'm going to go up through -1, cross through, come to 0, bounce, go back up, back to 1, cross through, back to 3, cross through, and then meet up with that up arrow. That is your sketch. Pardon?
So it's like a camel.
A camel, yeah. All right. There's still a little more. Sorry. Last one. And this one will be different, so please pay attention. If you understand what I've done so far, great, but just pay attention. There's a little subtlety in this one that gets students. X minus 4 squared, x plus 3 to the 5th, x minus 8 to the 3rd. There's your function. So there's really good news here, and then there's not so bad news, but there is bad news. So let's start with the good news. The good news is that I gave you the function already factored, which means you can already tell me what the x-intercepts are and the multiplicity, so you can tell me crossing and bouncing. This is kind of boring. Let's make this one 4. Sorry, let's make that one 4. Those multiplicities were kind of there. So we got 2, 5, and 4 here. All right? So if I were to set that equal to 0 right now, do you understand how this would be relatively easy to just set each one to 0 and then look at the powers to figure out cross and bounce?
Yeah.
All right, so if that part's easy, what part's the challenging part? Left and right behavior. Because we don't have the degree and we don't have the leading coefficient, do we? Right? It's not there? So here's how we're going to do it. What you have to do is you have to go in here and you have to look at each of these and ask yourself, what is this really acting like? And let me illustrate the idea first in writing it down, but then I'll come back and I'll show you how you do it when you're doing one of these problems. If I were to take x minus 4 squared, wouldn't that be x minus 4 times x minus 4? Right? And then you would multiply this out. You get x squared minus 4x plus 16. And when you combine, you get x squared minus 8x plus 16. That's what would happen if you multiply that out, which I don't want you to do. When you look at this right here, what is the degree in the leading coefficient of this? 2. 2 in the leading coefficient is a 1, right? That right there is going to be multiplied times this next one, right? X plus 3 to the 5th. X plus 3 to the 5th means x plus 3 times x plus 3 times x plus 3 times x plus 3 times x plus 3. This is really a nightmare. When I put these two together, would you agree that the highest power I'm going to get out of this is x squared? And then the highest power I get out of these two is going to be x squared. And then the highest power I'm going to get out of this is going to be just a single x. And when I multiply these all together, what's the highest power I'm going to get out of this? 5, right? X to the 5th. Now, I'm not doing all this multiplication. I'm just thinking, what's the highest power of x I'm going to get out of this? X to the 5th. What's the highest power I got out of that? X squared. And what do you think the highest power you're going to get out of this one is going to be? X to the 4th. So what we can do is we can really just say, hey, look, this is like x squared. This is really like an x to the 5th. And this is really like an x to the 4th. And then you just add up all the exponents. 2 plus 5 plus 4, which is 11. This whole thing acts like, behaves like an x to the 11th.